Hello, this video is entitled Hypothesis Testing for the Mean. Population standard deviation is known, or also sufficiently large samples can also fall into this category if it's not known. But the hard, fast definition is that we would know the population standard deviation or a good approximation of it. Now, hopefully you've seen the intro to hypothesis testing video or have studied the content, so you need to be familiar with that before you can really get much use out of this video. In that video, we talked about the p-value, which I'll bring back up here for a second from those notes. And you see the p-value is the probability, if the null hypothesis is true, it's the probability of how likely the sample results are true. Meaning true in the sense of predicting the population value. And the smaller the p-value indicates less likely that to be true. So now we're going to use the results from the p-value, and we're going to compare it with something else that was learned in that video called the level of significance. That's a value that's given to us. It's also the probability of making a type 1 error. So here's the test decision rule means under what decisions rule do you reject or fail to reject the hoe. If the p-value is less than or equal to your alpha, then you reject the hoe. If the p-value is greater than alpha, then fail to reject the hoe. It's highly unlikely they're ever going to be equal, but that is the definition. Usually you can probably get away with just saying less than or greater than for the most part. But to be accurate, it's less than or equal. Now the first thing we're going to do is find a p-value for a two-tailed test statistic with test statistic of z equals negative 1.72. Now also in that video, the last intro, we talked about finding the p-values, whether it's left-tailed, right-tailed, or two-tailed. Now when it's a two-tailed test, the test statistic may turn out to be positive, may turn out to be negative. And the rule we gave there was, okay, whether it's positive or negative, and here it's negative, but I would have done the same exact thing if it would have been positive, is we look it up as a negative, we find that area under the normal curve, and then we multiply it by 2. Because it covers both ends. It covers the negative and the positive end, regardless of whether the value itself was negative or positive. So if I look up negative 1.72 on the chart, come down here, there it is. It's 0.427, but I have to double that. Multiply it by 2, our p-value is going to be 0.0854. Now, let's decide whether or not we're going to reject the null hypothesis, the hoe, given a level of significance of 0.05. Now what I always do is, since you see how this definition was written up here, where it's written with a p-value on the left and the alpha on the right, that's the best way to compare your numbers, because that way you won't get the inequality symbols reversed and make a mistake that way. For example, you can say that 2 is less than 3 also means that 3 is greater than 2, which that's true. But if you have the arrows pointing the wrong way, it might be confusing. So as long as you put the p-value on the left, put the alpha on the right, since that p-value, 0.854, is greater than 0.05, we fail to reject the hoe. Now suppose that the alpha was given as 0.10. And we wanted to decide whether we reject or not. We put 0.854, put 0.10, And this time that number would be 80854 would be less than 0.10. So we would reject if that would have been the alpha, given alpha. Sometimes these decimal things can be a little tricky. What I often tell students to do is if you want to move the decimal over 4 places to the right on both sides, and then you could compare them as whole numbers that way if you wanted to. This one isn't too bad. I think it's fairly obvious, but when you start getting extra zeros in front of it, I'll show you where that could be a little tricky coming up. But so if you move these over for this one, what would happen is you would have 854 on the left side, you would have 1,000 on the right side. Then you can clearly say that 854 is certainly less than 1,000. Now this p-value would probably drive a statistician kind of nutty there, because you hate for it to be totally dependent on what the alpha is, especially if they're looking for a reject. If they're looking for a reject, they want this thing p-value to be really, really small. Or if it turns out not to be reject, you want it to be like a little bit larger than what we got even, because that way you would clearly not reject. Now keep in mind the p-values are probability, so they're between 0 and 1. So when I say larger, for example, like 0.35 is considered a large p-value or something like that. You'd hate to have one, if you were trying to determine this yourself, where it kind of wedged in between those two numbers like that. And here's where I mentioned about being between 0 and 1. And I got this out of the textbook currently using at this time, the Donnelly textbook. And you don't have to memorize this. You can use exactly the techniques I was just showing you. But I like this little phrase here. It says, if the p-value is low, then the hoe must go. And that's kind of rule of thumb here. Very, very low p makes the hoe reject. Now we're getting ready to start looking into some problems where we have some data. And I mentioned, we've talked about, even a few minutes ago, with that one example, we've talked about the idea of a test statistic, but we haven't seen how it's calculated from data. Z-test for the mean. Here's our formula. That formula probably looks familiar to you because it's the same formula, essentially, how you calculate the z-test when you're using the problems involving the central limit theorem, whenever x bar is our random variable. Except the only difference is here we have a mu naught instead of the mu. We're not given a population mean. That's the only difference. But the formula, so you have that standard error on the bottom, you're dividing by standard deviation over the square root of n. The mu naught will be so the x bar goes first. As the sample mean, the mu naught will be whatever we're testing against, whatever's being claimed. Now there's two methods for performing a z-test. One of them is using p-values, and the other one's using rejection regions and critical values. So we're going to start out with using the p-value method, which we've already learned what the decision rule is on the p-value, about the less than and greater than. But here's a problem with some actual data, so let's see what happens. All right, one of your distributors reports an average of 150 sales per day for the distributorship. You suspect this average is not correct. So you randomly select 35 days and determine from the number of sales each day. The sample mean is 143. With a population standard deviation of 15 sales. Given a level significance of 0.01, is there enough evidence to doubt the distributor's reported average? All right, now I just wrote some kind of the important numbers from the problem down here. So the n is 35, that's your sample size. The x bar, the sample mean, is 143. Population standard deviation sigma is 15, and level significance of alpha is 0.01. Now, we've got to get the hoe and ha set up properly here. So this also was talked about in that intro video. Remember, there's 3 possible hoe-ha setups there. Now, what I would look at is this sentence right up here. Sometimes it waits to the end to tell you. Sometimes it tells you at the beginning. Average of 150. Of is like is. It both implies equal. So this is going to be an equal. So you see that and you read that to be equal. So it's equal, not equal 150. Now the reason why I labeled the claim, which is not real critical, it'd still be the same either way, is yeah, their claim is 150, but we're the one that's performing the hypothesis test, so we suspect this average is not correct, so we're claiming that it's not 150. That's a little bit tricky. I try to avoid that as much as possible in the wording there, but you would still get equal, not equal, no matter how the claim was labeled, so it wouldn't make that much difference. So we're claiming that it's not 150. And equal, not equal was defined in that first section as a two-tailed test. So here's the test statistic, and this is just basically plugging numbers into a calculator here. So the X bar, got to get the numerator in the right order. That's your 143, your sample mean, minus the mu zero, what we're testing against, which is 150, divided by 15, which is standard deviation, divided by the square root of 35. And you see I just did that right there in the calculator, which any scientific calculator could handle that. And I get negative 2.76. So whether this had been positive or negative, I would look up the negative 2.76 on the normal chart. Negative 2.76 is right here. It's 0029. So, because it's two-tailed, we're going to have to double that number to cover both ends. So 2 times 0.0029 gives me 0.0058. So now I need to decide whether or not I'm going to reject or not reject. And to do that, as we saw a few minutes ago, you put the p-value first, you put the alpha second, then you decide the inequality symbol that goes here. 0.0058. Now I didn't put, so that's okay. I didn't put less than or equal to here, but that's kind of implied. In this case, it's not a tie anyway. Is less than 0.01. Now this is an example of one that might could be tricky. Like I was telling you, you might want to move the decimals over because you see that 5. I've got to go, hey, 5 is bigger than 1, but the extra 0 in front makes it a smaller number. So if you do that little trick I said about just moving the 4 decimal places over to the right, if you need to do that, you would have 58 on the left side, you would have 100 on the right side, and then it would be clear that 58 was less than 100. But that's only if you need to do that. So we're going to reject the hoe. Therefore, if we reject the hoe, we support this alternative. There is sufficient evidence to support the claim that the mean sales per day is not 150. Also from that last section is keep in mind that in this kind of stuff, when you fail to reject, that does not mean you support the hoe. It just means you don't think there's not enough evidence to dispute it. But the stronger statement is here, is when you reject the hoe in favor of the alternative. Then you strongly feel the alternative is correct. Okay, let's see how to do this in the calculator. All right, so we go right here. Clear that out of here. Stat. Test. Now, sometimes students will get confused if they're taking an exam that happens to have both confidence intervals and hypothesis tests on it at the same time. And they'll pick the wrong thing here and wonder why their input doesn't look right. It's real easy. 7 and 8, interval. Interval means confidence interval. Test means hypothesis test. So sometimes they'll just be doing something involving Z and they're not paying attention to whether it's hypothesis test or confidence interval. To pick the wrong number here, then nothing looks correct, which it shouldn't be because it's not what you're trying to do. So test for hypothesis test, interval for confidence interval. So it's pretty straightforward. Now your distinction, of course, is choosing between the Z and the T, which this video is not going to include the T test, but you've probably already seen that involving Z intervals and T intervals. All right, so let's Z test. Enter. Stats, because we're entering the data values, we're not using raw data. The value we're testing against is 150. The standard deviation is 15. $143. N is 35. Now, this is the important part right here to get the p-value right. The next line, those are the three possible ha's, the alternative hypothesis. You know, each ho pairs up with a ha. They didn't need to put both ho and ha here. All you got to do is, you know, because if you have a ho-ha setup, you're going to know what the ha is. It's either going to be a not equal, a less than, or a greater than. This one, our ha is not equal. So it's already happened to be selected there. So you have to pick the right ha, or you're not going to get the p-value correct. Calculate. 0.0058. Now, one thing to keep in mind this one's pretty accurate, but when you're doing these in my math lab homework, I hope it accepts that the fact that if you do it this way, it's not always going to be the same as the answer that you get using the chart, because it's going to take the z value like this and it's going to interpret the p value from there. So it might be a little off, so I'm hoping that the calculator answer will be sort of there and be included in my math lab's program in addition to just looking up on a chart. Now, that's not going to be an issue in one of my exams because it's usually going to be based on the chart answer, but the other answers wouldn't be that close to it. So if this was just a little bit off, it wouldn't make you miss the problem. But those of you that, you know, are taking a course that uses my math lab, you understand sometimes those discrepancies can cause an issue here. So watch for that. All right, so that takes care of that now. Now, one thing I'll just mention on this example before I move on is that, you know, you might be tempted to look at this and go, if we're testing 50 versus 150 versus not 150, and you get a sample mean of 143, you might just think, hey, 143 is not 150, so problem's over. No, it doesn't work that way. Everything else is part of it. If it did work that way, we would just do it that way. But, of course, the farther away from it is, the more likely you are going to lead to rejection. But it's not based on just that. It's not that simple, in other words. It's not just based on that. So it involves all these other factors. In fact, if I just change this real quick, and let me go stat. I'm just curious if I changed it to, let's say that sample mean was 148 instead of 143. Closer to 150, but still not equal to 150. I can't tell off the top of my head, but there's a chance this will be fail to reject. Oh, big time fail to reject. So that p-value of 0.43 would be way greater than the alpha. So that means we would have failed to reach. So in other words, that sample mean of 148 combined with everything else would not have been enough for us to say we felt that the 150 was wrong. We would have not disputed it. But 143, with everything else, did make us dispute the ho in favor of the ha. So it's kind of intricate how all that works. You have to use all the pieces to make this work. All right. Sprinkler systems fire protection claims the average activating temperature is at least 135. To test this claim, you select 32 systems. Activation temperature, the average temperature is 133 Fahrenheit with a population standard deviation of 3.3 Fahrenheit. Given a level significance of 0.10, do you have enough evidence to reject the manufacturer's claim? All right, at least. This is where we have to interpret that into a symbol. At least means greater than or equal to. Greater than or equal to. As we learned in the intro video, anything with an equal is a ho. That means greater than or equal to. less than or equal to, or equal. All right. So there it is, and that's the claim. They were claiming at least greater than or equal to, and based on what we saw in the last section, there's only 3 acceptable hypothesis pairs here. Greater than or equal to will pair up with its complement of less than. So we're deciding whether or not we reject this claim in favor of the alternative. All right. So once again, using the concept of hypothesis testing, if we don't reject it, that doesn't necessarily mean we agree with it. It just means we don't have the evidence to disagree with it. All right, so I just wrote down all the pertinent numbers right here from the problem. That shouldn't be hard. Level significance, once again, that's always your alpha. Figure that's new. The rest of these you should be able to figure out from reading the problem. So here's the ho and the ha. And then here's the test statistic. This is called a left-tailed test. So when your ha is less than, that's a left-tailed test. When your ha is greater than, that's a right-tailed test. So we put these in the formula. Of course, if you're using the z-test, you can do that, obviously. But 133 minus 135 divided by 3.3 over the square root of 32. I didn't actually show the calculation here, but you can check that if you want to. But I got negative 3.43. And since this is a left-tailed test, it's area to the left, negative 3.43, which means it will be the exact number off of the chart. So I look up negative 3.43, or if it's off the chart, you can basically use 0.001 or just 0. If it goes off the chart on the negative side, you can pretty much guarantee it's going to be rejection. 3.43, whatever it was right there, so super, super small. 0.003. And I'll show you the calculator thing here in a second. But actually, I'll just leave the screens here, and maybe we'll do a different one here shortly. But I want to point out something from the calculator output. So here's your p-value is 0.003. Your alpha was 0.10. So then we decide what symbol goes here. It's less than. So if your p-value is less than your alpha, you reject the ho, which means we reject the claim that the activating temperature is at least 135 degrees. So we disagree with it completely. So z-test, everything's pretty much the same as before, except for what right here. Look where I've got this arrow. You have to choose the correct alternative hypothesis symbol here. The last problem was not equal. This one is less than from right here. Less than. So you get your output. Now this kind of, people don't like this. This does sometimes these smaller numbers, it shows them in scientific notation. So what this e, the negative 4 means is if you start where that decimal is and you move it 4 decimals to the left, 1, 2, 3, 4, it's going to give you 3 zeros right in front of it. So it's basically giving us that same 0.0003 that we got off the chart. All right. Now, all right, so on this Texas 8th grade math score here, math exam, random sample of 85 students, has a mean score of 282 with a population standard deviation of 35. I'm sorry, it's actually on a national mathematics test, not state. This test result prompts the state school administrator to declare the mean score for the state's 8th graders on the exam is more than 275. Given a level of significance of 0.04, is there enough evidence to support the administrator's claim? Alrighty. This is pretty clearly worded here. More than 275. More than means greater than. Greater than is the alternative. It pairs up with less than or equal to. And now this is what's called a right-tailed test. Now notice the wording on this when it says enough evidence to support the claim. In this case, the claim is the alternative. To support this claim, the hoe will have to be rejected in favor of that alternative. So rejecting the hoe means we're supporting the claim because the claim is the alternative. So now let's do the calculation. Okay. All right, n is 85. The sample means 282. Population standard deviation is 35. Level significance 0.04. Here's the z-test. It'll be x bar 282 minus 275 over 35 divided by the square root of 85, which is 1.84. So we are absolutely expecting the test statistic to be positive for any right-tailed test. Because actually it would be a poor setup otherwise, poor design. Let's say, for example, if this sample mean was like 260, well, there's no way you can test that it's possibly greater than 275 if the sample mean is not already greater than 275. So that's where you would end up with a large p-value, fail to reject. So that's why, a properly designed test, you're expecting the p-value to be, for a right-tailed test, to be on the positive side. Just like for the last one, which was a left-tailed test, it was on the negative side. All right. So, to look up area on the right, we learned that back in the normal distribution era there of looking, we flip it up. Well, you can do it two ways, but the most popular and common way was to use symmetry and look it up as negative 1.84, flipping it over to the other side. So negative 1.84 is right here, and it would be 0.329. Oh, one thing I forgot to mention in the last one, we didn't do anything wrong, but I'll mention it now, and this also covers the last one. The last problem, I did not multiply that area on the chart I looked up by 2, and I do not multiply this one by 2. We only multiply it by 2 if it's an equal, not equal to tail test. Now, that's if you're doing it using the chart. If you're using the z-test, you don't multiply anything by 2 because it's already done it for you. I'm just talking about if you're doing it this way. Well, this one you still wouldn't do by 2, but don't double what you get if you're using the z-test, even on two-tailed tests, because it's already doubled it. All right, so 0.0329, that is less than 0.04, so p-value less than alpha, and we would reject the hoe and support the administrator's claim that the mean test score is less than 275. So once again, let's see, here's everything. The mu 0 is 275, standard deviation was 35, x bar is 282, n is 85, and then we picked greater than. That's the key right here, greater than. And you see it even spits it out here. That's one way you could check. When this output comes out, make sure that looks like your ha. Right there. It will match your ha. Now here's an example of what I was talking about earlier, is that using the calculator versus the chart, the p-value, if you did 4 decimal places, is 0.0326. It's just because it's interpreting that z-value and calculating that probability more sophisticated than we are by just using 2 decimal places on the chart. So I'm hoping that the MyMathLab homework will accept that answer, 0.326. Let's say it was just asking for p-value, I would hope it would accept either 0.329 and 0.326 both. But if you're having trouble getting answers correct, that's my guess. is it might need the chart answer. Hopefully not. All right, this is one of these tricky word interpretation problems here. Sometimes these are more difficult than calculations. All right. Coin-operated laundry, current owner claims over the past 5 years, the mean daily revenue was $675 with a population standard deviation of 75. Sample of 30 days reveals daily mean revenue of $625. If you were to test the null hypothesis that the daily mean average was $675, so that $675 is kind of treated sort of like a population value. So we're saying it, you're testing against $675, even though we find out that it is $675. And you did not reject the null hypothesis. What can you conclude? So this would have been an equal or not equal, because when it says was, that's just the past tense of is. So it would still be equal or not equal. It'd be equal or not equal. And if we got 625, and that still was not enough to reject the null hypothesis of 675, if we did not reject, that means there's not enough evidence to conclude that the mean was not 675. In other words, not equal. In other words, we can't reject the null hypothesis of equal to say it's not equal, because we could not conclude it. This is not the best worded problem out there. I could do a lot better job with this for testing purposes, but the main thing is it said we did not reject the null. So that's all that really matters, is that statement right there. If we don't reject, we can't conclude that it was not 675. All right. All right, this is interesting question here. I like this. Suppose you're given the p-value for the hypothesis test of 0.036. Now, can you conclude, should the hoe be rejected at the following levels of significance? 0.10, 0.05, 0.01. Now, there's several ways you can go about it. You test it one by one, and all we're doing is just comparing the p-value to each individual level of significance. So the first one, p-value of 0.036 is less than 0.10. So we're going to reject. P-value less than alpha, we reject. So that basically eliminates answers A and B, and we're down to C and D. The next one, put 0.036 on the left, put 0.05 on the right, and you still have less than. 0.036 is less than 0.05. We reject. So that one's yes. But for the third one, 0.036 would be greater than 0.01. So therefore, p-value is greater than alpha, we would not reject. So therefore, that would be no, not reject. So that's what makes answer D correct, with yes, yes, no. We would reject at the first two, but not the last one. Now we're going to look at the other technique using rejection regions and critical values, which is going to be the primary technique we're going to use for t-distribution problems. So we're going to throw the p-value business out the window for now. And we're going to be using some chart values here. Now this is showing this area now is not p-value. This area is alpha, the level of significance. So in a left-tailed test, that's going to correspond to a z-value off of our chart. And then if it's right-tailed, it's going to be a positive value because it's going to be over in this right side. So the values for the z for left-tailed and right-tailed are the same number, except one of them will be negative and one will be positive. For two-tailed, it's alpha over 2 on each side, half, because together they add up to alpha. So it's going to be whatever chart value represents alpha over 2 on the left, alpha over 2 on the right. Now we call these rejection regions, that shaded area right there. Because then what we do after we indicate our rejection region, and we'll talk about the rejection rules for this in a minute. I should have it written out coming up here, but let's see. Yeah, there it is, formally written out, but we'll see it here in a minute. But that means your test statistic still comes into play here. That's the only thing common between this and the p-value method. So if your test statistic on the number line here falls where the shaded part, on any of these, where that shaded part is, either here, or in either end there, if it falls into there, you're going to reject the hoe. That's called the rejection region, because if it falls into here, you reject. If it falls into the big empty region, we're going to say do not reject that hoe. So that's what we're basically saying right here. If it falls in the shaded region, reject. Otherwise, fail to reject. Now we're going to use the same table. It's actually called the t-distribution, but remember from confidence intervals, the z numbers are in the top row. Now you got to be a little careful how you read this. Now confidence level was easy because we just had one row of numbers there, whatever. But here you've got something called one tail and you've got two tails. So let's see what this is all about. One tail values represent alpha for whether it's left-tailed or right-tailed. But here's what you have to realize. And this picture hopefully will help, whether it's T or Z, this is going to be the same story here. All the numbers on the chart are positive. But when it's left-tailed, you're going to have to realize you're going to have to make your number negative. It's going to be negative for sure if it's left-tailed. But at one-tailed covers both left and right. It's just the left will be negative. If it's left-tailed, it'll be negative. If it's right-tailed, it'll be positive. Now, two-tailed, there's always two critical values here, a plus and a minus. Two critical values. But those alphas values are on the two-tail row. But so you got to be real careful which row you're on, because there's three of these, for example, that share the same number. Like you got a 0.1 here on the one tail, and you got a 0.1 on the two tail. So, oh no, you got to be careful which 0.1 you're looking at then, isn't it? I mean, that's no good. So long as if you pick the wrong one, it's no good. Okay, and then there's a 0.05 and a 0.05. And then a 0.01 and a 0.01. So we have to be real careful with that. All right. So let's see. As long as we do that, we're going to be okay. And let's go back. Oh, yeah, right. I was in the notes. I thought I was on a separate page there. So here they are written out. So here's the decision rules for this. If it's a left tail test, you're going to reject the hoe if Z is less than negative Z alpha. If it's to the left of the negative Z, you're going to reject it. Right-tailed, you're going to reject if Z is greater than the test statistic. And if it's two-tailed, you're going to reject if it's either less than the positive, less than the negative, or greater than the positive. Means if it falls in either end. Remember from back up here? Let me go back here. See, there's two shaded ends for this one. So obviously a single number can't fall in both of those. at the same time. That doesn't matter. If it falls in either one of them, it's reject. If it falls in the middle, it's fail to reject. So those are what we call our decision rules for this. So now we're going to try out some problems using this method. Oh, here we're just stating, okay, first of all, we're just practicing reading the chart and stating the decision rules. So this says, suppose you have a left-tail test, alpha's 0.01. What will be your rejection rule using this method? So you see, if it's left-tailed, it's going to start out with this verbiage right here. It's going to reject the hoe if z is less than some negative z value there. So now we have to go to the chart. So first thing, it's automatically going to look up to the part with the inequality right here. I mean, you can automatically write that down, but now we need to find the appropriate number from the chart. So left-tailed from the chart, that is one-tailed. Very important, we pick the one-tail row. One-tail, 0.01. Be careful not to confuse 0.01 with 0.1. 0.01, one-tail, and then there it is right here. 2327. So it's important that we did not pick the two-tailed 0.01 number. That would have been the wrong answer. So we're going to reject the hoe if your test statistic z happens to be less than negative 2.327, which I just kind of drew a graph of it here. Now suppose it's right-tailed and alpha's 0.10. Well, the beginning of this decision rule will be written like this. Reject the hoe if z is greater than some number, and it's going to be a positive number. Right-tailed is going to be a positive number, but both left-tailed and right-tailed, I can't say that enough, are both under the one-tail category. So it's 0.10, one-tailed, right there. 1.282. Now two-tailed, 0.05. Two-tailed is always going to be written like this. You're going to reject the hoe if z is less than some negative value, or if z is greater than some positive value. And they'll be the same value, it's just first one will be negative and the second one will be positive. So all we have to do is go look at the chart, two-tailed 0.05. Of course, it's only going to show one number there, but we just have to know that that's going to represent both going to be a plus and a minus. And here it is. There's two-tailed 0.05 right there at the bottom. And it's 1.96. So that gives us reject the hoe if z is less than negative 1.96 or if z is greater than 1.96. All right, let's try an example here. CEO of firm claims the mean workday of the firm's office staff is more than 8.5 hours. All righty. Pretty straightforward. More than means greater than. Greater than would be the ha. And it would pair up with the less than or equal to. And by definition, when they have a greater than for the ha, that is a right-tail test. So that's our claim, the greater than. So if we're going to support that claim, we're going to have to reject the hoe. All right, here's all the pertinent sample data from the problem. Sample 35, we had an average mean work day of 8.8 hours with a standard deviation of 0.5, and alpha was 0.01 level of significance. So we're going to do this problem using this method. So here's our decision rule. Because it's right-tailed, it's going to start out as reject the hoe if z is greater than some value. So this is 0.01's my alpha. It's 0.01. one tail, which that number already happens to be there, so I'll leave it. Right there below that block right there. There's 0.01, one tail row. And there it is, 2327. So we're going to reject that hoe if Z turns out, the test statistic Z that we calculate, if it turns out being greater than 2.327. If not, we'll fail to reject. So all we have to do is calculate the test statistic. You can use the formula, or you can also use the Z test to give you the test statistic. Even though we're not asking for the p-value here, the output always gives you the test statistic. So it'd be 8.8 x bar minus the mu naught, which is 8.5, over 0.5 divided by the square root of 35. I get 3.55. And so you see I drew the little shaded region right there. And you can see that 3.55 is to the right of that. So it's greater than 2.327. Or as I rounded it 2.33 here, that doesn't matter. Since 355 is greater than 233, we reject the null hypothesis and we support the claim that the mean workday is more than 8.5 hours. And you see here it is. And you can see that I chose where it says mu greater than 8.5. That shows you that I chose the, that one's that not equal one from earlier, but I chose the correct alternative hypothesis there. Well, anyway, I just want to show you the p-value here in this problem, since we have been learning that. Once again, e to the negative 4, you just move it over 4 decimal places. And it would be 0.00019. So if we were using the rejection rule we had using p-values, we would say that p-value is less than that alpha, and therefore we would reject the hoe. Because sometimes students will ask me, is it possible that to get reject by one method and fail to reject by the other? Well, it's possible, but that means you did something wrong. In other words, you didn't do it correctly. You can't do it correctly and have that happen. So it's going to yield either reject by both methods or fail to reject by both methods. So a mistake was definitely made if you got reject one way and fail to reject the other method. All right. I guess this one's not specifying the method there, but I did both methods on that one. I'm just looking ahead here for a minute. Yeah, so coffee shop claims mean caffeine content of 140 milligrams per cup. Of means equal. So this is definitely going to be an equal. Not equal hypothesis statements. Two-tailed. You want to test this claim. So here's all the important information. We have 42 cups. That's your N. The mean caffeine content for those 42 cups was 146. Population standard deviation of 22. And alpha equals 0.05. Okay. So let's look at the decision rule by using this method. Alpha's 0.05. Let's bring it up right here. Alpha's 0.05, but I already haven't been highlighted. 0.05, two-tailed. So you got to make sure you're in the two-tail row here. Very important. And there it is, 1.96. But when it's two-tailed, there is always a plus and minus 1.26. So we're going to reject the hoe if the test statistic Z is either less than negative 1.96 or greater than positive 1.96. And I'm using the test statistic formula here, 146 minus 140 divided by 22 over the square root of 42 gets 1.77. Oh. Now I did the test statistic in the calculator, of the z-test. And you see the z equals 1.77. And notice that I drew 1.77, but 1.77 is clearly in the middle part here. It's not in either rejection zone. It's in the middle. So we fail to reject. So just to give you a refresher of the kind of the concept behind this. That doesn't mean we totally support their claim. It just means that we do not have the statistical evidence to dispute it. So in other words, failing to reject the hoe does not mean we love the hoe. It just means we can't dispute the hoe. Now here's the p-value. I did the p-value it was already in the calculator, but if you did it using this method, it would be shaded both ends, and you would look up negative 1.77 on the chart. Which is 0.384. But because it's a two-tail, now we're back to two-tail, we haven't seen that in a while, we would double. So 2 times 0.384 is 0.768. And it yields to the same conclusion, like it's supposed to. 0.768 is greater than 0.05. We fail to reject the hoe. But here's another thing that I hope that does not cause you any difficulties in my math lab homework. But it's not that, the p-value is a little bit different from the calculator. Not way different, but a little different. 0.771 instead of 0.768. Hope that doesn't cause any problems. Fast food outlet claims that the mean waiting time in line is less than 3.5 minutes. A random sample of 60 customers has a mean of 3.4 minutes. Based on previous studies, we can assume the population standard deviation is about 0.6 minutes. If the level of significance is 0.05, test the fast food outlet's claim using critical values and rejection regions. All right. Claim was less than, so the wording wasn't too tricky there. That's the way I like it. Less than is a ha, always. Pairs up with greater than or equal to, and that was the claim. So if we're going to support this claim, in this case, we would have to reject the hoe. That's a left-tailed test. Here's the pertinent information. Oh, that should say, pause it. So N is 60, population standard deviation is 0.6, sample mean is 3.4, and alpha is 0.05. So using decision rules, it's a left-tailed test, so you always start out with reject the hoe if z is less than some number. So let's go to our, we're looking at one-tailed, 0.05, one-tailed, 0.05, but we have to make it negative because it's left-tailed. One-tailed 0.05 covers both left and right, and it's 1.645, but it's negative 1.645 in this problem. So we're going to reject the hoe if z is less than negative 1.645. Now, if you calculate the test statistic, that's pretty straightforward. We've done a few of these already, so I'll kind of skip past that, but I have everything labeled out right here. You get negative 1.29. And so here's negative 1.645. It can be kind of tricky with negative numbers on how to place where they go, relation to each other, and positive's pretty easy. But to figure out which side of negative 1.645 and where negative 1.29 go, it goes where I put it right there. But if you weren't sure, what you can do is you can use the symmetry of the curve and just flip everything over to get a feel for it better. So you make negative 1.645 positive 1.645. You make negative 1.29 become positive 1.29. Then that would be, I think, easier to visualize that 1.29 is certainly not greater than 1.645. But it's easy to mess that up with the negatives. So anyway, we have, then that's clearly in the fail to reject. So we fail to reject the null hypothesis, which means we do not support the claim that the mean waiting time is less than 3.5 minutes. Because we would have had to have rejected the whole, like I said earlier. And just for grins, here's the p-value, which 0.98 would have been greater than 0.5, so that also means fail to reject. So either way, we would fail to reject. Okay, we'll take a look at this last example. And I'm not using a tablet, so I really can't write much here, but I'll just kind of talk through it, or maybe just put some scribble here. Not too much, but trucking firm, lifetime of a certain tire. Actually, I'll tell you what I'll do is I'll go up here and copy this one. I think it's another left-tailed from, if I read it, maybe, hope I didn't read it too quickly. Yes. Claims it's less than. So evidently they're a little upset with their tire manufacturer here. Of course, now I gotta, well, that's still the claim. So much for neatness now. Now it's about to get ugly here. Actually, well, all right, well. This is 34,000. I don't even care about changing colors there. All right. 34,000 here. So it's a left-tailed test. And I'll just go ahead and do this one. It doesn't say which way to do it, by which method, but I can just go back to the p-value method. But I'll too hard to write it out, but I can verbally say what we'd be doing the other method. It's one tail 0.05, and it's left-tailed, so we're going to reject the hoe. Well, there it is right there again, same thing, same everything. We would reject the hoe if it's less than negative 1.645, the test statistic. But I'll just use the t-test in the calculator. All right, so stat. Yeah, we haven't entered one of these in from scratch for a while, so this will be good. So this is 34,000. And stat. Yeah, let's see, 54 is N. And mean is 33,550. Oh. I'll jump around. 33,550. Oh, 550. I'll double check that when I go back. 54, 30, okay. Standard deviation of 1,200. Now, the important part right here, which one of those three? I select the appropriate the alternative, which is less than for this one. If you pick the wrong you would actually, the test statistic still calculates the same way because the test statistic's not dependent upon the hypothesis. It's just a calculation. But the p-value is, and it would calculate the wrong area for you if you pick the wrong one. Calculate. So I said that if z was less than negative 1.645, well, negative 2.76 would definitely be way less than negative 1.75, 1.645, excuse me. This would be less. Also, the p-value takes care of it. 0029, we don't double, we never double it in the calculator anyway, but 0029 is clearly less than the alpha of 0.5. So 0029 is less than 0.05, and we reject the hoe, and we support their claim that the average lifetime of this tire is less than 34,000. And now that concludes this video for the hypothesis testing for the mean standard deviation known.